So I'd like to thank the organizers for this webinar to invite me for this invite me to have a chance to share some of this research progress that happening in my group, as well as introducing my research field, which is two-dimensional materials, to you. And I know this is a webinar form, so sometimes that interaction is not too easy, but I hope that you can ask the questions and through the chat or QA sessions, and hopefully that after seminar that we can have a little bit more interaction throughout this chat or the Q&A, or that kind of speak directly and ask the questions. Okay, so the 2D material research has been around for probably kind of close to about now, I think kind of close, getting to the 20 years sometime soon. And this 2D material research is starting from the discovery of the graphene, and then that a lot of exciting properties related to graphene actually comes around 2004, starting from the 2004. And the way that you get the graphene is exfoliate the graphite crystals down to one monoatomic layer of this carbon, what you call the graphene. And that was the initiation of this 2D material research field. Over the past probably 15 years or so, that the community discovered that more of this example of the 2D materials. And right after graphene, similarly to the graphene, that there's hexaboron nitride. It's a layered crystals of this hexagonal arrangement of boron and nitrogen. And again, the weak van der Waals force can hold them together. You can break these materials down to monoatomic layer. Unlike the graphene, which actually is direct material with a linear dispersion relation, hexaboron nitride is known to be a very good insulator or semiconductor dielectric. And soon after this hexaboron nitride, community realized there is a series of the material that similarly, that all the chemical bond is within the layer, but between the atomic, this layer, it is weak van der Waals force to hold them together, such as the metal dichalcogenide, the transition metal dichalcogenide is a good example. Some cases high temperature superconductor, and soon that this list got expanded into the that some sort of metal phosphorus trichalcogenide, even just the metal organic framework, some of this metal organic the compounds, and the list in fact grows almost kind of every week that we've been seeing that new arrival of this 2D materials. I think that's kind of interesting part. And of course, these 2D materials depends on the host crystal that you're starting from. They comes with various different type of the material properties. It can be different electronic properties such as semiconductors, metal, superconductors, some cases like the charge dense wave, like the strange metal, or sometimes it goes with the insulators, sometimes it becomes magnetic, even including the topological insulator. List of the different electronic properties or other physical properties also grows, right? Perhaps the most exciting, the opportunity on beyond that this diversity is because of this weak van der Waals force, hold them together. In principle, you can just put two different type of material together to make the interface between them without consideration of this the chemical incompatibility, usually which is a big the issues that when you just kind of create some sort of heterostructural material. And hence that this kind of stacking of this type of the materials in different sequences and different functionality to come up with this quasi three-dimensional structure becomes one of the really exciting possibility or opportunity of this research field. It is not only this simple the PowerPoint demonstration. Over the time, people indeed demonstrated such heterostructures can be built. You can try to grow these materials, but also you can simply break this material, as shown in this example, down to monoatomic layer. And one by one, you can just pick this material using this weak van der Waals force between them. And you can come up with this stacks of this van der Waals material in some sense by designing, by just kind of you decide which order and which sequences you just pick up the materials. You can quickly build up this the arbitrary sequence of this van der Waals system. And if you just do it really carefully, as demonstrated in this work, you have this interface. For example, your graphene is in between the boron nitride crystal. As you see, the interface is extremely atomic scale clean, and no impurity got trapped in between. And yet, atomically abrupt interface can be formed in this type of the system. Furthermore, you can choose different sequences and different shapes. This allows us also that you can selectively etch this crystal and make the contact in such a way that each individual, the atomic layers, as long as if it is electrically active, you can choose the right chemistries and the right recipe of the metal. You can in principle contact these materials by designing. So although these materials can be atomically separated only atomic distance away, in principle, you can just kind of make the contact, individual contact on this type of the system. And that will allow us to kind of probe this system in the two-dimensional form or the heterostructure form. In this particular example, the graphene in between boron nitride is a good example that the community has developed a way that you can make the selective contact onto graphene layer and make quickly the device out of graphene. Now that the quality of such two-dimensional system you can realize in graphene has improved over the period. Now that mobility or the mean prepath of the electron that in the graphene encapsulated boron nitride exceeds several hundreds of microns easily, as long as it's kind of low temperature. So this type of the ability of the creating two-dimensional system, especially in heterostructure form, immediately allows us to build up the rather complicated or interesting the quantum devices. Here, I'm showing you some of the example. In this particular example, that we have the two graphene layer, bottom and top and bottom, and separate by the thin boron nitride. If you just put very thin boron nitride, it can serve as tunneling barrier. If you put the reasonably thick boron nitride, few nanometer, you cut out the tunneling, but you still have the Coulomb interaction between the electrons in the top and bottom layer that can create some sort of correlation between them and drive this system the quantum mechanically unique system. For example, you can also replace the graphene with the, say, semiconductor. In this particular case, we have the P-type and N-type transition metal dichroic semiconductor, such as molybdenum and tungsten diselenide. Make the PN junction, so atomically thin PN junction. You can think about this atomically thin PN diode, which also, again, that can be controlled by the top and bottom gates to their the chemical doping, the carrier doping levels continuously by just using the gate voltages. You can actually continue this to make the kind of even more complicated devices. In this particular device that I'm just showing here, somehow my mouse control is a little bit too sensitive today. In this particular example that we have the P-type semiconductor, N-type semiconductor, again, touch with the N type of semiconductors with separation of each of the layer with the thin boron nitride, which actually also have the via channels to make the active channels there. Again, copied by the top and bottom graphite gate. You can see that there's about 9 different van der Waals layers going through the system, and yet each of these electrically active layers get contact. And this is a good example that one can build up rather complicated devices by just stacking. By just designing, you can come up with a kind of rather interesting functioning devices, as shown in this example. Right, this type of the example goes on quite a bit. But instead of I just kind of bore you that with kind of showing a lot of devices, let me just focus on some of the interesting physical phenomena and then give you some of the examples that based on this type of the van der Waals heterostructures. The example that I'm going to share with you is about the macroscopic quantum states that can be realized in van der Waals system. So this macroscopic quantum state is often that what many physicists got really excited about. Part of the reason is that this macroscopic quantum state often can be stabilized in rather macroscopic scale because of this rather robust quantum process. And those examples of this macroscopic quantum state include the superconductivity, Bose-Einstein condensations, and the superfluidity. All of these examples is in fact kind of demonstrate that you can build up this rather macroscopic states of the quantum condensation. It is robust in the sense that you can just see these materials, this type of phenomena by the bare eyes. as long as they kind of stay as condensation form. The key of the creating such a macroscopic quantum state robustness is coming from, in fact, the Bose-Einstein condensation. Here, that all these physical phenomena that we got excited about, behind of this, the phenomena, there's always kind of common, the fact that this comes from the bosonic condensations at the low temperature. Now, of course, all this, the so-called bosonic particle we are talking about, is not the fundamental bosonic particle. It is, in fact, the fermionic particle that constitute together to form this composite boson. For example, in superconductivity, which is condensation of the Cooper pair, the Cooper pairs are made of the two electrons making the pair, right? Same thing as the Bose-Einstein condensation of the cold atoms. Each constituent atom of the atoms consist of the electron, proton, and neutron. These are all the fermions as a fundamental particle, but they form as a boson, and they can condensate into the Bose-Einstein condensation. As you see in this example, that the creating some sort of the composite boson is a very important, the first step to realize this condensation-induced macroscopic quantum state. In fact, this comes from the composite boson. There is a way that if you control these constituent fermions, especially how this fermion forms the composite boson, you can actually alter their status of the condensation and form the macroscopic quantum state. A good example has been explored by the cold atom community, the atomic molecular optical physics community. In there, they can form the bosonic particle by starting from the two fermionic the atoms, controlling their interactions by Feshbach resonance, and they can form this boson, sometimes tightly bounded if this interaction is strong, or that they can be loosely bound if the interaction is weak, and that can be controlled by just basically controlling the Feshbach resonance. What they demonstrated is when the molecules forms tight boson, the condensation going through so-called Bose-Einstein type of the condensation. But once that the composite boson is loosely bounded or weakly interacting fermions cases, their condensation is going through more like the BCS type of the superconducting like the transitions. They demonstrate that they can continuously tune this type of this nature of the condensation. Now, while this is very exciting, that kind of physical phenomena that could be quite interesting to learn, it could be in principle very useful if you just realize this type of the phenomena in the solid state form, such that we can build up the devices out of it, right? In fact, in the condensed matter physics area, there has been some discussions how to realize such the bosonic condensations in BC or BCS type of crossover region. And that's the way of the using so-called the composite boson, which called the exciton. So exciton is kind of well known that in semiconductor physics, basically when you have the semiconductor, shine in, especially if it is intrinsic semiconductor, shine the light into the intrinsic semiconductor, you can excite the electron from the field band to the unoccupied band, and then make this hole in the valence band. And this remaining valence the band hole with this conduction band electron can be coulomically interact to each other, and they can form this hydrogen-like bound state, what you call the exciton. Of course, eventually the electron can be combined back to the hole and just kind of give the lights back, and that's basically how the exciton can emit the light, and that will determine this the optical property of many of the semiconductor, and that's why exciton is important. But if you assume somehow this recombination process is rather slow, or that even better if you just prohibit, this exciton as a composite particle of the boson can condensate into the exciton condensation, right? Theorists, in fact, actually study about those kind of limits. What if that indeed exciton lives along, and if you just have this controlled exciton density, such that compare with the size of the exciton, if you control the exciton density, which control the distance between the exciton, you can just kind of get into the so-called BC limit, where that all these excitons are reasonably well isolated, that this exciton can condensate into the so-called the excitonic Bose-Einstein condensation. Often people call the exciton condensation. But at the same time, at the different limits, if you just somehow pumped in more of the exciton, such that distance between the exciton is kind of really comparable to the size of the exciton, basically the constituting electron hole in the exciton start kind of screen each other and make this binding energy weak. So in high temperature, they can just unbound into the electron hole plasma. In the lower temperature, those kind of electron hole plasma can be degenerated and eventually can condensate into the superconducting like condensations, right? So as you see in this example, in fact, by controlling the exciton density, you may be able to see that so-called the exciton BC to the BCS type of the condensation by just controlling the exciton density. While this has been really beautiful, the theoretical proposal, experimental realization was rather difficult. And part of the reason is exciton is always exciting states. They can always try to recombine and kind of decay away, giving the lights out, right? So making this extra lifetime extremely long is rather challenging, except there has been some of the efforts. For example, that in semiconductor heterostructures, you create exciton in quantum well, but they embed this exciton quantum well into the optical cavity, and this exciton can start to resonate with this cavity photon, and then you can create this combination of the excitonic state with the photonic state, often called this exciton polariton. And if you just control the density and the temperature, this exciton polariton as a composite boson can condensate into the exciton condensation states. In fact, you just don't have to use even using the light to just kind of create this exciton polariton condensation. You can excite the photons by just lasing this quantum well, and just through this lasing effect, you can just combine this exciton polariton again, electrically excited the system. All of these things exactly create this exciton condensations, the exciton polariton condensation state, which is quantum coherent. So this is one way you can create another way of creating coherent light source. But as you see here, that while this is a really exciting first step to show, in a sense, this you feel like, well, this is very close to laser. In a sense, a small difference is that this is, in a sense, a laser in just interact with the exciton. Therefore, while this is, we can call the exciton polariton condensation, it has a very similarity with this kind of laser itself, which is kind of, you can call the photonic condensation, right? However, the idea that we can take out from here is, what if we make this exciton lives really, really long? We don't necessarily need the cavity to do that. And if we indeed create this just exciton condensation, this is one way you can create it, the system with this coherent light source like the laser without any laser cavity. I think that's basically one of the driving force behind of creating this exciton condensation to be useful for the kind of developing new way of this quantum light source. Again, in past 2 or 3 decades, in semiconductor heterostructure area, that this has been tried out. The important idea is, can we actually make the exciton live long? And there is indeed a way. In principle, that if you have the 2 quantum well and create the exciton in one of the quantum well, bias this quantum well, you can separate the electron hole in the one quantum well and move this electron and hole that live in the different quantum well. But nevertheless, this 2 quantum well is really very close by. So the electron hole can just kind of, although they live in different quantum well, bind together, form this exciton. And this type of exciton, since the electron and holes are separated spatially, the recombination rate is low, therefore they can live quite long. Using this type of the interlay exciton, in fact, the semiconductor physics community developed that way that pumping a lot of interlay exciton optically, they start to see that this interlay exciton can start to kind of develop the self-coherence, which is the very first step to realize about this exciton condensation. However, as you see here, that this interlay exciton is a really interesting way to push, because of semiconductor quantum well that you can make the MB system is relatively still broad. Size of exciton is still kind of large, and they have the enough overlap such that their lifetime is not necessarily really long. I mean, it's longer than without interlayer, but it's not. It's still kind of several hundred nanoseconds at the most, with a very weak binding energy, which means that these are kind of relatively low temperature physics rather than technologically relevant. However, here comes the one example that I can demonstrate indeed using this 2D material and the heterostructures as an immediate advantage, right? So here is one example. If you just have this semiconductor TMDs with, say, various transition metal combination with the charcoal gene atoms, depends on your choice of the metal and the charcoal gene atoms, you can pick up the various different type of band gap and band alignment between this 2D system. Particularly that if I just choose a moly diselenide and tungsten diselenide and P-type semiconductor, put them together, they are atomically thin and make the really sharp interface, but nevertheless, they are separated by the Van der Waals gap. And electron hole that living into the both of the layer doesn't necessarily readily recombine to each other. And especially if you just choose the right size of this band gap, they can form so-called the type 2 band alignment, which can be extremely useful to realize about this interlayer extern. Indeed, in past few years, that we've been realizing this heterostructures atomically thin PN junctions. And once you shine the lights, you can create this interlayer exciton, forming that electrons and holes in opposite layer of the TMD layer. They live quite long because, again, it's very similar way of this interlayer exciton than in semiconductor structures. They are living the different layer, so they don't necessarily recombine fast. Lifetime can be controlled by the gate voltages. Furthermore, there, the energy level can be controlled by just kind of gate voltage by applying the electric field. Furthermore, not only you can just create this electron hole, the exciton, by shining the light, since electronic device-wise, this is nothing but PN junction, PN diode, you can inject the carrier, positive and negative carriers into the N and P type of the semiconductors. By just injecting the electron holes, you can force them to form this interlayer exciton. And in that way, this interlayer exciton can form, and they recombine it and they give us a light, and it turns into this light emitting diode. So in some sense, you can generate this interlayer exciton by the electrical means. Also, you can interrogate those kind of property of the interlayer exciton by observing the light emission from the devices. And quite recently, there's a kind of further exciting demonstrations in there. In the previous device I just showed, it's PN junction. Although their lifetime is long, something like a few hundred nanoseconds, they are not infinite yet. The paper the work done by the Cornell's group, led by the Kim-Fai Mark's group, beautifully demonstrated that if you just insert the additional layer of this boron nitride, you can make the interlayer exciton's lifetime is even longer. And of course, here that interlayer exciton can be formed by electron hole injection, as I mentioned. And then by just biasing, then you can just get the tunneling current. And when the tunneling current is flowing into the system, they see the light comes out, although that is not the direct light coming from the interlayer exciton. It is coming through the so-called intralayer trion, but nevertheless, just observing this light emission from this device, as well as this carefully measured capacitance, they show that there's a strong indication indeed that there is an interlayer exciton coupling happening, and they may actually condensate it into the macroscopic quantum state. And that this condensation temperature is not necessarily extremely low, it's something like the tens of Kelvin or 100 Kelvin, right? Indicating that indeed this can be quite kind of the way that you can create the robust, the excitonic states out of the system. Of course, a really direct proof that one can try to make is, can I just look at this interlayer exciton directly and see whether they have the really some sort of quantumness in there, the quantum coherence in there, right? So we actually expand this work even further. Instead of now using thick layer of the boron nitride, we can just insert only one layer of the boron nitride, one atomic layer of the boron nitride. So that will still give you enough separation between P and N junction, such that exciton can live longer. But more importantly, that now that they can also, with a small bias, tunnel back to the recombinations of the electron hole can be controlled by the bias voltage, and you can get the direct lights out from this interlayer exciton. So by just observing the light emissions that correspond to the interlayer excitons that beautifully shows up in this type of the spectrum, and looking at their quantum statistics, then you should be able to tell that whether there is a really quantumness going on. Indeed, we just kind of take this light up coming from the interlayer exciton, and then we just kind of using this Hanbury-Brown and Twist second-order correlation measurement, and indicating that indeed that right before the thresholding behavior happens, there is an increase of the quantum correlation. So the G2 factors, which means there is a kind of correlated effect appears into the system. But once that kind of sudden, the threshold behavior with a sudden increase of the really bright light source comes up, you see that G2 correlation completely quenched to the 1, which actually indicate there is a coherent process actually going on right after this increase of the quantum correlation. All of these things indicating indeed that there can be quite intriguing cases that happening like this, the coherent light source development due to this external condensation. Of course, this is not yet the really smoking gun type of the demonstration because you have to really show the spatial and the temporal coherence of this condensation itself, which actually we are trying to do. But at least this shows a really important step forward to creating this external condensation type of behavior. What you see in this example, that although there's a kind of really encouraging progress that's happening, is it kind of keep struggling that how you can control this lifetime versus that this coherence into the system. And part of the reason that this type of the struggle to create this external condensation is basically exciton, as name indicating, is not a ground state. Basically, it is always happening by the excitation, either light or the electron hole injections. And therefore, that the creating this thermodynamic ground state limits where condensation should happen is in some sense is analogical. It can never be achieved in these quasi-equilibrium cases. However, there is a interesting way that you can create this ground state external condensation, slightly different way. In this particular example, that we can still use this double layer of this quantum well, but instead of using their semiconducting gap, you can use the Landau gap, where that it forms by applying the strong magnetic field, which quantizes electron motions and open up the gap into the day energy spectrum. And often this Landau level and the Landau gap formation is that the basic ingredient to create this so-called quantum Hall effect, one of this most quantum mechanically exciting transport phenomena. Now, here that using double layer, but approach is slightly different. Instead of you create the Landau level and field up to Landau level to get this quantum Hall effect, in this particular cases, you leave this both of the Landau level close, kind of separate by the spatially, it partially filled. But it's partially filled, but it's complementary partially filled. In other words, each of the density, if you add them up, you basically have the filled Landau level, which means that if you somehow take these two, the Landau level in the two different layers and make the projection, they can form the one full Landau level as a single layer, right? So imagine that you have the very small separation between the layer, the top partially filled layer, the bottom partially filled layer. There is that kind of develop the correlation or between them, such that there is the organization of the electron hole in both of the layer, which actually the way that when there is electron in top layer, electron get avoided the bottom layer to create a hole in the bottom layer, and they can just kind of bound together almost, right? So form like the exciton, like the states. Now, this is handy waving arguments, but you can go through the kind of complete, kind of accurate mathematical structures. And if you just write down the coherent wave functions that describe this complementary field Landau level, where the correlations start to happen. In fact, this macroscopic the wave function exactly follow that wave function that you expect to see in the external condensation state. And that's basically the way that we can create the external condensation like the state by just using the magnetic field. In fact, this type of the experiment was done again in semiconductor heterostructures almost 20 years ago. Example showing here the Jim I. Jensen's group at the Caltech in the late 90s, early 2000s. the group beautifully show that indeed the partially filled Landau level can form this entire full Landau level. And there's a kind of strong Coulomb drag effect appears in this two layer, indicating that this two layer got coupled. Few years later, that few other groups, including that now Mensur-Seigen's group at Princeton and Kliching's group at the in the MPI in the Germany, they show that it's not only that two layers coupled that strongly coupled to shows this Coulomb drag effect. If you connect this top layer, the bottom layer, such a way that current flowing one of layer is going against the current the other layer, and this is so-called counter flow geometry. If indeed extern magnetic extern forms here, and if they condensate it, extern itself is a superfluidic state and can flow without any dissipation. Now, if the extern is flow, electron moves in that way, hole moves in the same way, which means the current is moving opposite way. If we just kind of flow the current in the counter flow geometry, that counter flow current geometry, you expect to see that there's no dissipation. It's almost like the superconducting state. And indeed, this has been also demonstrated into the quantum Hall bilayer beautifully. So what we can do is we just basically, similar to that extern condensation case, we just copy down that idea developed into this semiconductor heterostructures, but simply replaced by the 2D materials. In this particular case, now we have the two graphene layers separated by the boron nitride, such that applying the magnetic field that both of the graphene layer that start to develop this Landau level. We want to couple the electron hole in the partially filled Landau level to form this magnetic extern condensation state. And experimentally, we can measure this condensation state, as I said, measuring the counter flow resistance, right? Because if the magnetic extern is condensated, we expect to see the zero, the counter flow resistance. And that's kind of how the measurement is happening here. Let me show you the data that in this, the graphene quantum well, separated by the 2 nanometer of the boron nitride, and apply the magnetic field. We just create this magnetic condensations. And I'm showing you that the resistance or counter flow resistance measured in this system as a function of magnetic field and temperature. Here, the magnetic field will control that the magnetic extern density because they are separated by the magnetic length scale. So as you increase the magnetic field, the more and more magnetic extern sits in and their distance becomes smaller. Therefore, that you just drive into the more so-called the BCS type of the magnetic extern states. Now, what you see in this data, that the blue color is where that you get the zero counter flow resistance. This is condensation state. If you go to the higher temperature, it becomes finite, you get this normal states, right? So you can clearly see the low temperature, there are something zero counter flow resistance state shows up. As you go to the higher temperature, they becomes kind of finite resistance state, which is kind of expected. But what you see here is as you change the magnetic field, they shows this nice dome like this phase boundary. You now start to see that this dome like the phase boundary is what actually theorists expected to see that in the extern condensation. So already you start to see that indeed we can realize this type of extern condensation phase diagram simply because that in this graphene, the quantum well, since you put these two quantum well very close, the energy scale is much larger, and you start to see that this type of phenomena is tens of Kelvin rather than millikelvin temperature ranges. That's exciting. But more interesting part is when we just kind of look at their transition behavior at the different magnetic field, especially when you get the high magnetic field where you have a lot of extern density such that the transitions appears as like the BCS type of transition. Indeed, transition is sharply happens like the superconducting, like the transitions. What is the kind of theory expected to see in this type of the BC and BCS type of the crossover in the system? So this actually gives you that another example that by just combining on this van der Waals system, one can realize the macroscopic quantum state, which can be rather robust. And that's actually brings up the kind of interesting physics in there. Now, besides of these two examples I shared with you, in fact, putting the van der Waals heterostructures that provide yet another very exciting opportunity. And that even doesn't necessarily need to go for the heterostructures. Imagine that I have the one single graphene layer or TMD layer as shown here, right? I think I mentioned that I can just stack these materials together, form these heterostructures and different functional properties. but instead of putting another layer on the top to form the heterostructures, we can just kind of make the same layer on the top, but with a slightly different angle. And this is so-called the twisted the stacking of the system. As you see here, by just changing this stacking angle, although this is the same material together, they form some sort of the quasi-periodic structures, what we often call these Moire structures, right? And these Moire quasi-structures can be controlled by the stacking angle, and that's a way that we can engineer some additional periodic structures larger than atomic length scale. In fact, this type of Moire engineering has been used already in kind of several years ago. For example, graphene on the top of the boron nitride, again, very similar materials, they form these Moire lattice structures. And applying the magnetic field in these Moire lattice structures, you can create it, so-called this fractal quantum Hall effect, which actually is strongly related with this the self-recurrence of the fractal energy band structures, what you call the Hofschild butterfly-like the structures. So these are kind of some of the examples. Indeed, you can just create those kind of Moire engineering. But what is kind of rather exciting part is quite recently, about 3 years ago, 4 years ago now, right? The group led by Pablo Harriero at the MIT discovered that if you just tune this twisting angle into the graphene, something like what they call the magic angle, right at the magic angle, suddenly graphene turn into the insulator, so-called correlated insulator. More exciting part is if you just dope this correlated insulator, they start to see that this correlated insulator developed the superconductivity. In fact, this type of this new phenomena was what theory expected 10 years ago by just considering that the combination of the van der Waals structures, Moire structures, with the small interactions across these van der Waals interactions that can engineer band, such as a kind of flat band. And once that this flat band appears in this magic angle graphene bilayer, there are a lot of exciting physical phenomena appear, such as superconductivity. And later that many other groups found that not only superconductivity, there are magnetism, there's some correlated effect, and all sort of different type of the physics arises by simply just kind of putting this two layers together, right? But it turns out this is basically just a starting point. You don't have to even stop at the 2 layer. You can go for the 3 layer and 4 layers in different type of combination with just on the top of the twisting angles of the control. You start to see that superconductivity and magnetisms and all sorts of different physical properties start to appear even just using the graphene alone. But it's not only graphene alone, that you can just kind of stack different systems. For example, that you just put the TMD layer together. Again, that you can just form this different type of the domain structures out of the Moire structures. But in TMD, because of different lattice structures, in each of the domain, actually has their own dipole moments in opposite directions, which create the excitons with a different type of energy control by the gate voltages possible. And this will bring us again that interesting new idea or new directions that you can create it exotonic system or periodically modulated exotonic system, again, by gate control. Things is not stopping only there. It's not only electronic property, nor the optical properties that can be modulated by the exotonic, the Moire structures. The another example is basically these Moire structures can also kind of change their dielectric, the ferroelectric properties. Since my time is almost up, let me just kind of quickly go through that, the last example. I'm showing here that one of these layers together, just kind of put them together with a small twisting angle, right? And we just put this sample under the TM grid, and we apply the electric field in the vertical direction. As I briefly mentioned, for this TMD layer, right, dark part and bright part correspond to the opposite domains with the opposite direction of this the polarization developed. So you can view that this is as if that there is a kind of interesting ferroelectric domain structures that tie together. And not surprising enough that when you apply the electric field in here, you can start to see that, let me just see, the control, those kind of domain structures and sizes, and sometimes the large scale of the domain reversal is happening. And all of these things is basically the way that we can engineer in the ferroelectric type of domain by just controlling this angle through the Moire engineering onto this type of the TMD lattice. So what you see here is that not only electrical optical properties, you can also change this the dielectric ferroelectric properties using TMD, the twisting the junctions. So what you see here is that some of the other example that you can yet engineer different type of physical properties that using the another now. So let me just kind of close down my talk with a kind of following slide. And as you see in this the table that I made this table about kind of 6 or 7 years ago. That's at the time that just that community realized how to form these heterostructures by just kind of picking a method I mentioned. And all sort of different type of interface can be conceivable, right? As I said, the graphene boron nitride, molybdenite, and those kind of things. Between their interfaces, either homo and heterostructures, there are various different type of physical phenomena appears, as I just kind of showed a couple of the examples throughout the talk. And as you see that as the different type of material kind increases, you start to see that a lot of different type of the physical phenomena is expected. But what I'm just arguing that is not enough of the stories. It turns out there is yet another axis. That is the axis that controlling this twisting angle, right? So if you just consider that those kind of the degree of freedom to controlling the twisting angle, even with the same or slightly different system, you get through that various different type of this the combined system with the different properties. So what you see here is a phase space. We can create different type of materials. This is kind of approaching to infinity. And here, the important part is not only the experimental exploration, but theory guide, especially where to look for. And those kind of theory guide is again also very important. Just kind of explore this type of the wide phase space. Okay, so with that, let me just kind of stop here. And the last slide that I would like to thank my groups that kind of working on various parts of the project that I just presented today, and kind of pushing this frontier of this 2D material research and the heterostructures. Thank you very much for your attention.